Hello. So I'll be talking about detecting supernovas with Python. So I'm Pippin. I do software at a company in Toronto called DESA. We spend a lot of time actually doing machine learning systems and kind of tools for machine learning people. And it was about a year ago that we actually started to kind of build out these tools and actually think about how we actually want to build this empathy for people. So along with a couple of colleagues and myself, we actually wanted to look at building a supernova detection model. But I'll first give you a brief background on how we got there. So at DESA, we kind of live and breathe Python. And we're always kind of working with our ML engineers to actually build these tools. And we're also kind of obsessed about space. We're constantly building model rockets and talking about space. And so really when we got the opportunity to build a machine learning model and kind of start to do some more experimentation with machine learning, we started a project called Space to Vec in order to kind of help us understand what machine learning was. What are the machine learning people on our teams actually feeling when they're doing machine learning? How is that process actually happening? What are the pain points that they're actually running into? There's also a really good excuse to learn about space and to kind of understand it. So we started this website called spacetovec.com. And the goal was really to ask, where is deep learning techniques useful in astronomy? And I think it's equally as important to kind of talk about the fact that we're actually not just interested in successful research. We're actually interested in documenting where it's not useful. In our field, there's a lot of talk about kind of AI and kind of what it can do. But we wanted to be very functional and transparent about the actual applications of it. You know, we actually wanted to show people that it's not magic. And there wasn't a lot of resources actually doing that right now. So we created this website and actually to kind of start to document that process and to make that more accessible. It's also a really great way to kind of give back to the community. And I think that's a point that actually Gray made last night, is that when we're kind of hiring people, we kind of talk about this magic skill set. And I think we're at a really interesting moment in time in the Python community where we're not really astronomy experts, we're not machine learning experts, we're just software developers. But we're able to kind of work on these projects thanks to the wonderful Python community, all the open source tools that are out there. And so in order to start our project, we did some kind of initial research. The way that we did that is we talked to a bunch of kind of astronomy people in academia, as well as reading a lot of papers on arXiv. And that taught us a lot of things in terms of actually understanding what the modern astronomer was like. For instance, in academia, they just recently switched over from using languages like IDL to using Python. And the whole problem with astronomy and academia is that there's not a lot of money in astronomy, right? People do it because they love it. All the astronomers that we talked to wanted to share what they knew because there wasn't a lot of other people, there wasn't a lot of resources to actually do this work. And so we essentially asked, where can we help out? And so we eventually found a lot of different GitHub repos showing that the community had kind of really adopted kind of the open source mentality. Researchers were sharing their code, and so they didn't have to duplicate work. So the other interesting thing we found out was that in the astronomy side, there's all these telescopes that are going to be coming on board in the next few years that are going to produce a lot of data. Over the last 20 years alone, we've gone from a couple megabytes a night to up to 30 terabytes with the LSST. And as engineers, that's going to create a lot of interesting problems in terms of dealing with data. So the problem. So there's this telescope that I kind of alluded to earlier, and it's in Chile. And the goal of this telescope is to take a survey of the sky and basically understand kind of the dark energy of the universe. So this is a very large task. And so the task that we kind of took on was following a paper that we found on arXiv. And this paper basically documented taking images from the dark energy survey and building a model to actually do supernova detection, specifically on type 1a supernovas. So these are essentially what would happen is astronomers would get this data, and they would want to quickly find the supernovas in the data. And they would be able to follow up and do deeper investigation into these supernovas. And so they built this application called AutoScan. And essentially, on the machine learning side, it meant taking images and feature engineering that into tabular form. And the data set was actually a binary classification problem. And basically, the 0 and the 1s that you see there in the object type refer to supernova or not supernova. And the data set was actually split about 50-50 in terms of actual data, and about 900,000 images. But this process that you see here in terms of actually doing the feature engineering meant that astronomers with specific domain expertise actually needed to look through the supernovas and actually the images and actually clarify if they were supernovas or not. And this is a fairly manual process, and it takes time. And so we asked, we work in this field called deep learning, and there's techniques that allow us to kind of just take images as they are and feed them into the model. And can we actually do it without feature engineering? Can we reduce this time that astronomers are spending and help them? And so the AutoScan paper had previously put out a certain metric, and so the goal was to kind of beat that metric without doing feature engineering, using a convolutional neural net. And the goal here was to obviously reduce astronomer time, so that time actually doing the feature engineering and deciding what features go into a model. And there's often that common phrase in software engineering that if you do a task twice, you should probably write a script for it. And so this is probably a bad analogy, but CNNs, you don't have to kind of do that manual task of kind of doing that feature engineering. You can kind of just feed in the images and actually do that. So as software engineers, we saw that as a great excuse to kind of automate things. I can't really talk about how CNNs work in this talk, but what I will say is they actually do build up these feature maps of kind of the interesting parts of an image that it's using to classify. So how do we do that? We spun up a quick AWS instance with a few Jupyter notebooks, and we used a bunch of open source tools. And again, I'll highlight, we're not astronomy experts, we're not machine learning experts, but there's a lot of tools that allow someone like us to actually do this kind of work, this really interesting scientific work. So we learned a few things along the way, and I think this was part of our journey in terms of actually doing the machine learning project, is understanding these painful points to doing machine learning. And one of those was actually on the Jupyter side. Jupyter notebooks are great for exploring information, but they're not so great for doing production work. This is a deep topic, and I'm happy to talk about it later. Jupyter notebooks are very good for certain things, though. It's also very difficult to organize results, and loading data every time was kind of painful. And so we built our model. It was 3 layers, and no feature engineering needed. And we ended up with these results. So this is kind of our false positive and false negative scores. And as you can see on the right side here, our scores are lower than theirs, which means it's slightly more accurate. So we're able to successfully use the CNN model to actually not have to do the feature engineering with the random forest model. So what does that mean in terms of actual images? It means that if you took about 900,000 images, you get the majority of those correct. And in terms of kind of laying it out, that would mean you would get 23 are classified as supernova, and they aren't. And 36 you would classify as not, and they actually are supernovas. So what do we learn from this? Well, as software engineers, we didn't actually see a lot of these pain points. We would often hear about them from our ML team, and we were actually able to kind of see why we're building this tool at DESA called Foundations to actually do model logging, to do data caching, and to actually understand how these production systems are so complex. We were actually able to feel that pain. It also kind of taught us to kind of the fact that we're able to actually do this within the open source world, thanks to all these projects. And you don't have to be an expert to do this. So I'll just leave you with this note. We're not astronomers or machine learning experts, but thanks to the Python community, and Holden did this really well in her talk, it's actually possible for us to do really interesting work in the scientific world. So these are the stars of the talk, if you're interested in more. I'm happy to talk about it more afterwards in terms of just the model and our results. We'll actually be publishing our official results next week if you're interested, if you go to spacetevec.com. And thank you very much.